Okay, we'll see the dual converter today. What is the dual converter? As we know that in the previous classes and all, we discussed single phase as well as the three phase controllers. In that, we cover the semi converter as well as the full converter. So there is a semi converter and full converter. So in the semi converter, we noticed that voltage is positive always. Obviously current is positive, so that will give only the first quadrant converter. Whereas in the full converter, if you observe that, it will give first quadrant and fourth quadrant. So that means alpha less than 90 degree, it acts as a motoring operation or rectification mode of operation. Alpha greater than 90 degree, it is a inversion mode of operation. This is a rectification mode of operation. And this is the discussion so far. If you want only rectification, we'll go for as a semi converter, whether it is a single phase or a three phase, no matter. And if you require both, that means if you required first quadrant and fourth quadrant, or else rectification and inversion, or a motoring and braking operation, then we'll select as a full converter. Because of unidirectional device used in a circuit, it will give only positive current. But whenever you require negative current, then you have to use as a dual converter. So that means there also you are using as a unidirectional device only. But the thing is the connection, we are interchanging that directions, but the current will pass from anode to cathode only. That is the dual converter. It is also called as a four quadrant converter, because all four quadrants we can get it using dual converter. So two fully controlled converters connected in anti-parallel will form as a dual converter. So that is the reason another name for this dual converter called as a four quadrant converter. So four quadrant converter or dual converter, both are same. Only thing is we are connecting two fully controlled converters connected in anti-parallel, that form as a dual converter or four quadrant converter. Now if you operate one converter, it will give two quadrants, and another converter it will give another two quadrants. So we'll get it as a or four quadrant operation. So that is the small thing. Now we'll see how this will be operate under single phase supply as well as the three phase supply, all these things. So as I mentioned, two full converters connected in anti-parallel to the same DC load, means load is a common terminal, and that will be as a dual converter. Such arrangement we call it as a dual converter. So what I mentioned, two full converters connected in anti-parallel in the same load. So that side is one converter and another side is another converter. Both are full controllers only. This will provide as a four quadrant operation without any mechanical change over the switch. We don't require any change over switch for operating first quadrant to fourth quadrant or second quadrant to third quadrant, like that. We don't require any changeover. By changing the firing angle itself, this operation is going to be takes place, depends upon our requirement. Only change is we need to change the firing angle, depends on our requirement. And here two modes of operation is there. One is a non-circulating current mode of operation, another one is a circulating current mode of operation. So non-circulating current mode of operation means there is another name for this, is a sequential operation or sequential control, and circulating current mode of operation simultaneous control. Another, these are the some books they represented sequential, simultaneous. Some books they represented non-circulating current mode and circulating current mode of operation. Anything is same. Only thing is here, as I mentioned, there is a two controllers are there, no? So let consider this is a one controller, one full controller, input may be single phase or a three phase, anything, and then this one is a load, it may be motor or a normal load, anything. and another controller is a opposite direction. We are connecting like this, and this two you can connect, and here is supply. So this is nothing but a dual converter. This is a controller 1 and this one is a controller 2, and come in between there is a load. So the simultaneous means both controllers will operate at a time, and sequential means one controller is operating, other controller is in the up state, like that. So at a time only one controller is going to operate. So our other name for that is a NCC, non-circulating current mode of operation. Another one is a CC, circulating current mode of operation. Nothing is there, these two are outputs are DC, no? Between load, if both DC source voltages are same, we don't get any circulating current. If that is the different, then obviously current will interchange, no? Current will pass to the one converter to other converter. That is only the circulating current. That's the thing. And we have their advantages and disadvantages. Even circulating current mode we have some advantage, and non-circulating current also we have some advantage. Similarly, both having their own disadvantages. Depends on our requirement of operation application side. We can select whether I have to go with this mode, NCC mode of operation, or a CC mode of operation. One major difference between these two is in the NCC mode of operation only one controller is operating at a time. That is the major thing, and lot of differences are there. Anyhow, I will explain that. And CC mode of operation is both controllers will operate at a time. That is the major difference between these two things while it is operating. And now there is a non-circulating type single phase and three phase dual converter configurations. We'll show that whether if we give or you can say that two single phase fully controlled converters connected in anti-parallel, that is a single phase dual converter, or two three phase full control converters connected in anti-parallel, that will form as a three phase dual converter. So that is only the controller we are using, whether you are using a single phase controller or a three phase controller, and we'll see that diagrams, all these things. Now normally everyone knows that single phase full controller, this one is a single phase full controller, this is also single phase full controller. Only thing is we are arranging this connection in the different version. So if we can see that this is plus and minus, now the current will pass in this direction in the next controller. That is only the difference. This is one single phase full converter, there is another single phase full converter, in between there is a load. This load may be motor or normal load. In drive subject we will use as a motor, or now also can use it motor, no problem. In between because why this is a 4 quadrant operation, no? Motor is preferably motoring forward motoring and reverse braking, and then forward reverse motoring, reverse braking, all this forward braking, all these things will come into the picture in the case of motor. So that's why generally on the application side we can act as a motor. And now you can see the another circuit, three phase dual converter. In this you can see instead of single phase fully controlled rectifier, if I use as a three phase fully controlled converter, then it is a three phase dual converter. And this is three phase fully controller, this is another three phase full controller connected in anti-parallel, will form as a dual converter. And another I told no 4 quadrant operation is possible. So as I mentioned, in the non-circulating current mode of operation, our simultaneous operation is circulating, and sequential means one by one. Now you can see that suppose if I operate only one converter, converter 1, everyone knows that what you call it as how this controller is going to operate. How this will be operating, suppose controller 1. Forget about all this circuit, this side circuit to just forget about, and I am connecting as a load here, and when it will give positive voltage, you can see if alpha is equal to or alpha less than 90 degrees, voltage is given as a positive voltage. And same thing, if I keep alpha is greater than 90 degrees, then what will happen? Alpha is less than 90 is positive voltage, and alpha greater than 90 degree, it is a negative voltage. So that means if controller 1, I am saying controller 1 alone operating, then if it is, I call it as alpha 1, controller 2 I call it as a alpha 2, just for differentiation purpose. And alpha 1 less than 90 degree, it will give first quadrant operation. Now whenever you require fourth quadrant operation, alpha 1 you can keep it greater than 90 degrees. That is the case if controller 1 is operating. And suppose I want to operate controller 2 alone. So they don't turn on this, you just give the pulse to the controller 2 alone. Now that I call it as alpha 2, represent the, or A and B, any notation you can follow, less than 90 degree, and you can see that current is passing like this and it goes T2 and then it comes out. So that means this will be voltage is negative, current is negative with refer to the reference. Current is passing anode to cathode only, but with refer to this reference I call it as opposite direction. That's why voltage is negative, current is negative, then the power is negative. Then I mean power is positive only, because voltage and current both is negative, then power is positive, then it is a rectification. So alpha 2 less than or equal to 90 degree, then we call it as a motoring operation. And similarly, if alpha 2 you make it greater than 90 degree, then it is a braking operation. Like that, if the controller 1 is operating less than 90 first quadrant and greater than 90 fourth quadrant, controller 2 less than 90 third quadrant, then controller 2 greater than 90 will be the second quadrant. So like this you can able to get all four quadrant operation if individually controller 1 alone operating will get first and fourth, controller 2 alone operating, you will get the second and third quadrant operation. But both should not fire at the same time. That is the case of non-circulating current mode of operation. That is why we are getting all four quadrant operation. Now we'll see when circulating current, why it is occurring as a circulating current, all these things explanation. Whatever I explained so far, it is only introduction portion. Now you can see that controller to work alone will get polarity. That's already explained. The load voltage as well as the direction of the load current with respect to controller 1 is reversed. That's why we can get it as a motoring operation in the third quadrant operation. So controller 2 can operate second quadrant and third quadrant. Controller 1 can operate first and fourth quadrant operation. Now, so ideal dual converter. So whatever I shown the diagram in the previously, what is the diagram will represent? We can see that controller 1 output. So forget about all other diagram. Controller 1 input is a AC supply, and finally we are getting as a DC supply. This is a plus and this is a minus. Input is a AC supply and output will get it as a DC. So now this DC is a fixed one or a variable one. Anybody? This DC is going to vary by varying a firing angle of a controller 1. That's why while I am representing the equivalent circuit of the dual converter, after this whatever I am getting variable DC supply, I mention as a controller 1 or V01. You want, you can make use of like this also, it because this is a variable voltage. How that is going to be vary? By varying the alpha 1. Like that, similarly for controller 2. So this diodes will represent the unidirectional current will pass like this. It is a load side. Similarly, we can see that this another controller current also will pass like this. There is a two controllers. In this case, our one assumption that controller 1 magnitude and controller 2 magnitude must be same with negative opposition sign. So the thing is, if I call it as a V01, it is directly parallel with the load. Let's consider this is a V out. If I consider this is a V out, what is the V01 value here? V01 is equal to the V load only because both are in parallel. That is equal to minus V02. That is our assumption that we are to put or set a firing angle such a way that magnitude of the controller 1 is equal to the controller 2 with negative sign. That means that polarities are reversed because we interchange that total controller itself. That's why the opposition sign will be there, but V01 is equal to the minus V02. Like that we have to provide as a firing pulses. So now we'll see that controller 1 and controller 2, suppose if it is operating like this, as you know that controller 1 alpha is 0. What is the output? Output of controller 1 is nothing but what? Whether it is a single phase or a three phase average output voltage. So what is average output voltage for suppose if we consider single phase? That is V01 is equal to what I can write? 2 Vm by pi into cos of alpha 1. What is controller 2 output? That is also full controller 2 Vm by pi into cos of alpha 2. And now we can see that at the load terminal, what I can get it V out that is equal to, or I can say that V01 is equal to minus V02. V01 is equal to minus V02. These two will get cancelled out. Then I can write cos of alpha 1 is equal to minus of cos of alpha 2. Then cos of alpha 1 is equal to this. What I can write, there is a 180 minus alpha 2. Then apply both sides cos inverse. Alpha 1 is equal to 180 minus alpha 2. Or simply I can write alpha 1 plus alpha 2 is equal to 180 degree. Even if it is a three phase, what change will be there? Instead of 2 Vm by pi into cos alpha 1, we will get it as a V01 is equal to 3 root 3 Vm by pi into cos of alpha 1. Then another one also same, this will get cancelled out again, same thing will get cos of alpha 1 is equal to minus cos of alpha 2. From that alpha 1 is equal to 180 minus alpha 2, or alpha 1 plus alpha 2 is equal to 180 degree. So that is the logic is required whenever both operating at a time. So that means this magnitude must be equal to this magnitude if you give alpha 1 plus alpha 2 is equal to 180 degrees. So this is only the thing. Suppose you can see that alpha 1 0 to 90 degrees it is positive, beyond 90 degree it is a negative. Similar fashion, you can see the alpha 2, this one is 0 and here is 90 degrees and this is a 180 degrees for alpha 2. So 0 to 90 degree, what we are achieving, there is a positive, and 90 to 180 degree it is a negative. So that is the logic here, and from that by seeing this, by changing the alpha 1 and alpha 2, how the controller is going to operate. So only one constraint is here, you must remember, if both want to fire at the same time, alpha 1 plus alpha 2 must be 180 degree, we need to satisfy. That means this magnitude is equal to this magnitude will obtain if you connect firing angle alpha 1 plus alpha 2 is equal to 180 degree. Common firing only, but only thing is once if we provide alpha 1 suppose 60 degrees, automatically the firing pulse to the controller 2 will generate alpha 2 is equal to 120 degrees. Like that you can able to generate the firing pulse. That's why generation of firing circuit is little bit complicated because it has to meet this logic. And then as I derived just now, if it is a single phase converter 2 Vm by pi into cos alpha, and then if it is a three phase, if I use line, that's why not use root 3. If it is a phase voltage, if I want in general, you can follow only one thing, this replaced by 3 root 3 Vm by pi into cos alpha. So this is the general expression. Now, based on in exam also, suppose if they ask explain the 4-quadrant converter, that is your choice. Either you have to use single phase or a 3-phase. Anything is correct. But specifically, if you ask the 3-phase dual converter, you must and should use the 3-phase circuit and waveforms. And then V01, this magnitude 2 Vm by pi into cos alpha, the 2 Vm by pi is a common, that's the Vmax maximum into cos alpha. So from that we will get it as a V out is equal to V01 is equal to minus V02. From that Vmax will get cancelled out. Cos of alpha 1 is equal to cos of 180 minus alpha 2. From that we will get it as alpha 1 plus alpha 2 is equal to 180 degrees. So this is the logic we have to use to satisfy our controller. Both is operating at a time. This will not be valid actually. Alpha 1 minus alpha 2 is equal to 180 degrees is not valid. Alpha 1 plus alpha 2 180 degrees, because if something here, why we are getting that is, here we can use as a plus or minus generally, because both cases this will be valid. No, minus cos alpha 2, I can write plus or minus, that's why it will get it. But we are getting only alpha 1 plus alpha 2 is equal to 180 degrees, because total alpha should not be more than the 180 degrees. That is the reason we can use alpha 1 plus alpha 2 is equal to 180 degrees. That's what I mentioned. No? The firing angle can never be greater than 180 degrees. So we can get this alpha 1 plus alpha 2 is equal to 180. This is the controller quadrant wise. First quadrant converter 1 will operate. Fourth quadrant converter 1 will operate. This, if you want, you can mention that alphas also. Alpha 1 less than 90 and alpha 1 greater than 90. Similarly, alpha 2 less than 90 and alpha 2 greater than 90. This way also you can mention. This is all 4-quadrant operation, at what instant which controller is going to be converted. Now we'll see practical dual converter. So both converters is operation. Firing angles are controlled in such a way that alpha 1 plus alpha 2 is equal to 180 degrees. So that means one converter is operating with some angle alpha 1, other converter must be 180 minus alpha 1. The average output voltage both must be equal, both average controllers are equal, but instantaneous voltages are not same. You can see that suppose two students percentage same maybe, but individual subject marks may be different. So the one subject may have the different marks with the other student, like that. Here to controller 1 and controller 2 average output voltages are same, but instantaneous voltages are different. Because of that different voltages occurred in any particular instant, then there is a circulating current will pass through the controller. So that is the problem. How to overcome that problem, all these things we'll see that. Voltage difference when two converters are interconnected, the results large current, large circulating current between the two converters. So that means we can see that simple. Suppose if I consider output voltage is like this. This average are same. If I consider first one and second one, both are magnitudes, 2 pulses. Here also 2 pulses. If you take average, will get this, and if you take average, will get like this. So, but if I consider particular instant, any instant, suppose at this instant, if I want to know what is the magnitude, you can see that this magnitude is maximum, this magnitude is 0. Or another instant, if I consider like this magnitude is 0, this magnitude is maximum, and like that it's gradually, it is decreasing gradually, it is increasing gradually, like that. So any particular instant, if I calculate or if I see the magnitude of controller 1 and controller 2 voltages, average may be same, but particularly instantaneous voltages are different. So that will give circulating current pass through the controllers. And particular any circuit limit to the circulating current. So because it is unwanted current, so lot of problems will be there, because of this voltages difference, there is additional current has to be carried the devices. Normally, while you are designing or you are selecting the device rating based on your load rating. Suppose our load rating is some 10 amperes. Based on that only we are connecting as a thyristor ratings also. But in addition to that, if the additional circulating current is there between the two controllers, who will carry that circulating current? These controllers only will carry. And then thyristor, apart from the load current, additional circulating current also has to carry. That is the problem. In that case, we need to use I rating of the thyristors to carry the circulating current. So preferably we need to minimize the circulating current because it is unwanted. So how will you minimize the circulating current? First question is why it is getting as a circulating current. Circulating current is obtained because of the different in voltages. And now same thing, there is a voltage source, this one, and here the voltage sources are magnitudes are different. This is 5 volt, this is 3 volts. Then automatically circulating current pass through that. To limit that circulating current, we make use of a large reactor. So that is the purpose we are using as a reactor like this. Now what I am doing is, that is the problem will arise. To overcome that problem, one large reactor you have to connect half of the reactor in this side and half of the reactor in the another controller side. In between there is a load. You can use the lower side also reactor. It's like this also if you want, you can use it. While you are doing lab and all, sometimes we'll use both sides to limit the circulating current or for safer side. So you can see that half of the reactor we can connect this side and this is a half of the reactor. So similarly for 3-phase also you can see whether it is a single phase or a 3-phase controller. Here you can add one more leg, you can connect as a additional reactor. So like that, now we'll see the these are the things so far we discussed. Now what we'll see is a explanation part of a NCC mode as well as the CC mode of operation. What is the difference we observed so far? In a CC mode means circulating current mode of operation, we required as a reactor. In the previous circuit we seen, no, in between we required as a, here we have to connect as a one reactor. So that is the thing. And whereas here reactor is not required because both controllers not operating at a time. Only one controller is operating at a time. That's why no chance of getting as a circulating current mode of operation. When circulating current will come into the picture, if both controllers are operating at a time, even though magnitudes are same, but instantaneous voltages are different. That's why between these two controllers there is a circulating current will pass. Now in NCC mode of operation, only one controller is operating at a time. So that means first I am giving firing pulse to the controller 1. What about the controller 2? You are not giving any firing pulse to the controller 2. Therefore it is open only because all the devices we are not giving any firing pulses, and then controller 2 is in the off state. So we are giving firing pulse to the controller 1 at an angle of something. Whatever may be alpha you want, you can put it alpha is 0 or 30 degrees or anything. You can put it even 90 or 120 or whatever, you can pass the firing angle. Then what I can get? You are getting as a positive voltage, positive current. It is a first quadrant operation. Whenever you require braking, you make use of this alpha 1. You can make greater than 90 degrees. Then automatically you are getting as a fourth quadrant operation. Now how to transfer from controller 1 to controller 2, because I want as a third quadrant operation. Let us assume that when I am operating first quadrant operation, controller 1 is operating, but immediately I may be required fourth quadrant, let it be as a third quadrant operation. Let us assume that. How will you transfer from this controller to that controller? Because first of all you must turn off this. How to do that? you have to remove the firing pulses. Once if you remove the firing pulse, or you can keep alpha is the highest value, then automatically magnitude will reduces to 0 level. Then disconnect the supply. Then what will happen? Ensure that all the devices is turned off completely. For that, you have to wait some time. That is a 10 to 20 milliseconds of time you have to wait. Even though if you remove the gate signal, but because of the inductor and all, it is continue to conduct some more time to ensure that we have to wait 10 to 20 milliseconds of time. That means that during that instant all the devices are going to be turned off completely. Then you can give firing pulse to the controller 1, controller 2. Now we are giving pulse to the controller 2, whether it is a 60 degrees or whatever may be the alpha you want, you can pass the firing pulse. Now we are giving pulse to the controller 2 and we disconnect the firing pulse to controller 1. Then based on mode of operation, whether you want second quadrant or you want third quadrant, you change the alpha to whether less than 90 or greater than 90, you will get it as another 2 quadrant operation. Again you require maybe first quadrant operation. Then what I had to do? Again disconnect the firing pulse here. Alpha you can to disconnect and supply you can turn off, and then you wait 10 to 20 milliseconds of time. Again switch over to controller 1. Again you have to wait some time and switch over to control like this. So what is the drawback? We noticed that one, the advantage case, we don't require any reactor between the two controllers. That is the advantage only. And obviously when the reactor is used between this, there is a voltage drop across that reactor and power loss takes place, then efficiency will go down if I use the reactor. But now if no reactor, automatically efficiency is going to be high. This will be high, and reactor is not required means cost wise will be less. And then devices using, while you are using as a devices, less rating devices are sufficient when compared to CC mode of operation. Their additional current has to carry the device, that's why we required high rating of the devices. But here only to meet the load current, thyristors are sufficient. That is the things. Now one drawback is there here. In every instant, if I want to switch over from one quadrant to other quadrant, you have to wait some time. Then while you are waiting period or dead zone period 10 to 20 milliseconds of time, what will happen? Your response will be 0. You are not getting any output voltage during this interval. So if the changeover, or what you call it as one quadrant to other quadrant changeover is required regularly, you cannot use this. If I use this method, automatically discontinuity problem will be taking place. So during this instant we don't get any output, no, that means current will be 0. That is the major problem. Dynamic response will be poor because of the time delay, 10 to 20 milliseconds we have to wait. That is the major drawback in this mode of operation. Same thing, if you want to operate for single phase circuit, you can draw as a single phase circuit. Explain only 2 points. One point is just only one controller will operate at a time. If the firing angle is given to the controller 1, whether it is alpha less than 90 or greater than 90, it will give as a either positive voltage or a negative voltage. Current is positive, then you will get first quadrant and fourth quadrant operation. Whenever we required as a second and third quadrant operation, controller 1 has to be turned off completely, or you can disconnect the firing pulses and wait for some delay time 10 to 20 milliseconds of time, and then you have to give the firing pulse to the controller 2 controller 2 going to be operate. Again you want to switch over, you need to wait for some more time, 10 to 20 milliseconds of time, and we have to give the firing pulse to the controller 1 by disconnecting the firing pulse to the controller 2. This is only the operation for NCC mode of operation. And if we require now single phase means you can use this single phase diagram. Explanation is same whether it is a single phase or a 3-phase controller. And these are the advantages and disadvantages. One major advantage, as I said now, both controllers are not operating at a time. That's why we don't get any circulating current. So only one current will operate at a time. That's why reactor is not required and losses are less. Then obviously efficiency will be high. This is the advantage. And disadvantage case, load current become discontinuous. Why it is discontinuous? One controller 1 to controller 2 or controller 2 to controller 1 vice versa, we are not transferring directly. We are wait some time. During that time, both controllers are off state. That's why response will be poor. Load current become discontinuous. And operation is slow because we require this much time between the two controllers operation. Now we'll go for as a CC mode of operation, circulating current mode of operation. In this, one logic must be required. What is that logic? Alpha 1 plus alpha 2 must be equal to 180 degrees. Like this, we have to draw the waveforms also. Because why both is operating at a time, no? Now what is the response of controller 1 and response of controller 2? Suppose they are operating alpha 1 is 60 degree and obviously alpha 2 must be 120 degrees. Then only this satisfaction will be there. And what is the average output voltage? Because both controllers are operating, controller 1 output voltage, controller 2, then final output voltage, then the reactor voltage, where the reactor between the two controllers we are using as a reactor now. And this is a one controller and this is another controller, and in between there is a reactor. So that's why we want to know what is the reactor voltage and what is the circulating current, IC. All these things we have to find through waveforms. So now we'll see that this is a single phase, because I told no question may ask either it is a single phase or a 3-phase, but in generally they ask explain dual converter with CC mode of operation. Then we can use your choice. Both I will explain, single phase CC mode as well as the 3-phase CC mode. And NCC mode, whether it is a single phase or a 3-phase, no waveform, only explanation part. Explanation is come. And now we can see as per this diagram, I want to draw the supply voltage, controller 1 output, controller 2 output, and average output voltage, and then voltage across the reactor. So all these things I need to draw. So for that, as you know that, suppose for example, to draw the waveforms, what I am considering is alpha 1 is equal to 30 degrees or a 60 degrees. Alpha 2 must be equal to 120 degree. Let's forget about the second controller. Only one controller with load is there. As you know that alpha is 60 degree, how to draw? Alpha is 120 degrees. How will you draw the waveform for controller 1 alone available? So now I will draw alpha is equal to 60 degrees. How will you draw at starting? This one and RL load, we are getting like this. And there is another way. This is the value of alpha is equal to 60 degrees. Normally only one controller is there. As you know that single phase full converter. Similarly, alpha is equal to something 120 degrees. What will happen? 120 degrees, where we have to put the firing pulse? At this instant, because this is a 120. It will continue to conduct up to next firing pulse, then like this. So this is your alpha is equal to 120 degrees. Now same controller 1 only I am telling. Now I want to make that in the controller 2, what is different? This magnitude and this magnitude is same, only opposite sign. Then what will happen? I want to draw, this is alpha 1 is 60 degree. Then obviously alpha 2 is equal to 120 degree. This 120 degree and that 120 degree, what is the difference? Only minus sign. So this will become as a positive. That will get positive, and then waveform will be like this. So this not required. Only just for understanding purpose, I drawn normally alpha is equal to 120 degree of controller 1, then same as controller 2 by putting as a minus sign. So once if you know alpha 1 and alpha 2, or you can say that waveform, output voltage waveforms, then I want to draw what is the average output voltage. How will you get the average output voltage? That is a V0. Whatever I drawn these two waveforms, V01 and V02. But now I want to draw output voltage. How will you get the output voltage? By looking this waveform or by seeing this circuit, we can know that V01, this is a V02. I want V out. So then we can easily get V out average of these two things. This is average of controller 1, average of controller 2. Then V01 plus V02 by 2 will give as a V0. Then how will you get the VR? Where is the VR? This is the voltage V01. This is the voltage V02. How will you get the VR? VR is equal to V01 minus V02 over. Like that, we have to add these two things by divided by 2 will get V out, and subtract these two things will get it as a VR, and then circulating current, total current is this I1, let assume that this is I1 current, and some current is passing in this, that is I0 current, and rest of the current passing through here, that is I2 current. So from this I1, that is equal to I0 plus I2, or we can see that I0 plus I2 is nothing but a circulating current. Who will supply now the circulating current? Controller 1 is going to supply the circulating current. This magnitude is more. Suppose if this instantaneous, I am telling that instantaneous voltages are different, only will getting as a circulating current. So therefore I0 plus IC will give as a circulating current. Or also I can mention secondary, controller 2 current is nothing but a circulating current. I2 is equal to IC, and we are to get I0. So this I0 and IC, how will you draw the current waveform? All these things we'll see. Now that is clear. Only thing is we are to represent any value of alpha. We start with alpha 1 is equal to 30 or 60 whatever. Then the rest of alpha 180 minus alpha 1 will give alpha 2, and these two average will give output voltage, and subtract these two V01 minus V02 will give as a VR voltage. And then once if you know the VR is nothing but what? Inductor voltage, no, LdI by dt. If we integrate this, we'll get it as a what is the circulating current directly. That way also we are getting as a circulating current. So now I will show that waveforms. Now we can see first three-phase supply, single phase DL converter, single phase supply. Now I consider alpha 1 is equal to some 30 degrees or 60 degrees whatever. I drawn the alpha 1. And how will you get the alpha 2? By 180 minus of this alpha 1 will give as alpha 2. That is what our condition. So alpha 1 plus alpha 2 must be equal to 180 degrees. Now I know what is the alpha 1. Then automatically alpha 2 is 180 minus alpha 1. This is the same. Just to understand in exam, this wave is not required. Only for understanding I drawn. This is 30 degrees. Then what will happen? 180 minus 30 degrees. That will be as a 150 degrees. 150 you make it, and we'll get it as a same controller 1 output. Now you reverse it. Then we'll get it as a alpha 2. So this is your alpha 2. You can consider, I will write here, this is a V naught 1. Is not required, just for understanding. This is a V naught 2 and this is a V out. Now we'll see by seeing this 2, and you forget about at this moment, it is not required. Only to understand your case, I drawn that. Just a minute. Now, so you can see this thing you forgot about. And only thing is V naught 1 and V naught 2. So what you have to do, V naught 1 and V naught 2 must add V naught 1 and V naught 2. You will get it as a V out. How will you get the V out? V out is equal to V naught 1 plus V naught 2 by 2, the average of these two. Then what is this thing? This is a negative and this is a positive. This plus this will get cancelled out, so we'll get 0. And now you can see this is a positive and here also positive. That will give doubles of Vm, 2 Vm by 2. We'll get it as a Vm. Same thing, we'll get this. And after that, what will happen? This duration is positive and this duration is negative. Then average, if I take 0, and here is negative and here is positive, average is 0. So that means this total is 0. And here is positive and here positive, 2 Vm by 2, we'll get it as a Vm. So like that, we can able to draw the output voltage waveform. So now we draw the voltage waveform. Now what we want to draw is VR. So we will get the VR. According to our circuit, VR is nothing but a V01 minus V02. That is equal to voltage across the reactor. Now we know V01 and as well as V02. Once if you know V01 and V02, you can subtract that, you will get it as a. Now we can see that this is V01 and this is a V02. This we can write V02. This is a V01. This one is V01. This is V0. So what? There is a minus. Let it be minus Vm, and then V02 it is positive, but sign is V01 minus V02. Minus minus get plus. So then what will happen? This will become, here is a plus, but minus sign is there. Then minus Vm, that is a minus 2 Vm. So that is with alpha. So now just I am telling, now what will happen? This is a positive and whereas this is a positive, I am subtracting. Minus Vm will be 0. So that's why we draw 0 here. And similarly, this shapes. So whatever V01 and V02 is there, you just subtract these two, will get it as a VR. So same thing. Now we can see that average output voltage 2Vm by pi into cos alpha, because controller 1 or controller 2 magnitudes are same. For controller 1, put it as alpha 1. Controller 2 case, put it as alpha 2. And just for CC mode of operation, alpha 1 plus alpha 2 is equal to 180. That the reason again I am using here. Both magnitudes are same. Then V01 is equal to minus V02. If I simplify that, we'll get it as alpha 1 plus alpha 2 is equal to 180 degrees. Now, how to calculate the reactor voltage, all these things. Now you can see that instantaneous output voltage are different. That is what large circulating current flows through the reactor. So to limit that only we are using as a reactor. So now output voltage by adding that controller 1 and controller 2 and reactor voltage subtracting V01 minus V02, and what is VR is inductor only, LdI by dt. Current is a circulating current through the reactor. To limit that circulating current only we are using as a reactor. Now we can see that integration VR with respect to d omega t, that's why I used it as a denominator as a omega, and if you integrate this, VR is nothing but V01 minus V02, V01 Vm sin omega t, V02 minus sin omega t, and I simplify this, just only simplification on small integration, and you'll get it as a final expression like this. Reactor current are nothing but a circulating current to Vm by omega Lr cos alpha 1 minus omega t. The circulating current will be maximum if this cos omega t is equal to 1. So that means omega t is equal to 2 pi will give as a cos omega t is equal to 1. This is another way also you can represent 2m by omega Lr 1 minus cos of alpha 1. That is also same because on the cos side minus or plus both is same. That is the general expression for circulating current. That's what I mentioned here. So circulating current will be maximum 2m by omega Lr into 1 minus cos alpha 1. Similarly, we'll go for as a three-phase circulating current mode of operation. In a three-phase circulating current, waveforms instead of single-phase waveform will represent as a three-phase full controller waveform. That is only the difference. This is very easy compared to the previous one. As again, same notation will follow. Suppose alpha 1 is equal to something what you call it as 60 degrees or something, you can take it 60 degrees, then alpha 2 is equal to 120 degrees. As you are aware that waveforms for three-phase fully controlled converter. In a three-phase full control converter, alpha is equal to 60 degrees. I mention all the alpha values. Suppose alpha is equal to 0, we'll get all the 6. 180. Suppose if it is 180, we'll get it as a negative side. This is 0 axis, we'll get like this. This is a 180 degrees. And similarly, for alpha is equal to 60 degrees, exactly it reaches to the natural pi. Like this, we'll get it as a all 6 pulses and so on. And suppose if it is a 120 degrees, what you can get? It is hanging like this. For controller 1, only one full controller I am telling. These are the waveforms I already drawn in the previous classes. Now, suppose this is alpha is equal to 60 degrees. This is alpha is equal to 120 degree. Now, for alpha 1 is I am keeping alpha 1 is 60. As usual, you can draw this. Alpha 2 I want 120. This is alpha 1 120, but alpha 2 120 means what I can do, you make use of this in the positive, just minus sign if you multiply. If I do that, what I can do, only thing is whatever negative portions are there, you can represent in the positive, same thing. So then what will happen, you can draw this alpha 2 is equal to 180 degree means that instead of getting negative, we are getting as a positive. You are getting like this. Then what will happen, this average is same, but instantaneous you can see this is maximum, this is 0, this is maximum, this is 0, and go on we are decreasing this and go on increasing, somewhere we are getting both the same, then the average what will get 0. So that way we can get it as a, in this case maximum will start and then this case will be 0 and again it will get it as a negative. So like that you are adding these two divided by 2 will give as a average output voltage. Similarly, subtraction V01 minus V02 will give as a reactor voltage. Again, you derive the expression for circulating current. Everything is same. Now you can see very simple. This is the line to line voltages directly drawn because already you know that how to draw the phase voltages, firing pulses, then line to line voltages. You can shade that, you will get it this. So in this case, even this also not required if you are able to remember alpha is equal to 60 degrees waveform. Exactly, it reaches as a natural 0 instant. And now alpha is 120. For controller 1, if I want to draw, this will getting as a like this for 120 degrees. Alpha 1 means controller 1 120. But now I want to draw controller 2 angle is 120. So what is, you just make it as a minus sign. If I keep minus sign, all this will become as a positive. That is only easy way to remember. You can see this is a controller 1, this is a controller 2. But now we can see all the things are 6 pulse converter, this magnitude Vm sin omega t, this is also Vm sin omega t. Then finally average will give same. But instantaneous voltages are not same. What is the instantaneous? You can see any particular instant, you can see this is a maximum. But what about here? 0. And here is maximum, but here 0, like that. So instantaneous are different. That's why you are getting as a circulating current. How will you get V out now? Anybody? How will you get V out? You add these two waveforms. This is a maximum plus 0 by 2. So that will give as a this one is go on decreasing, go on increasing. You will get it as some point of time both are maximum magnitude are same, this plus this, and we'll get it as a maximum, and then decreasing, then increasing, like that. So we are getting as a V out waveform by adding these two, or you can say I will write here V out is equal to V01 plus V02 by 2, because average that will give as a V out. And now how will you get the VR? VR is subtract these two. How will you subtract? You can see this magnitude is maximum, this is 0, this minus this, so then maximum. Then after that what will happen? It is decreasing gradually, it is increasing gradually. What will happen? This magnitude is same somewhere. If you subtract, 0 will get, then it is 0, and we'll come to here, this is 0 minus this, then we'll get it as a minus magnitude. Like that you can keep on adding, subtracting these two waves, automatically we'll get it as a reactor voltage will be like this. So once if you know the reactor voltage, and how will you get the circulating current? So you can see that based on the reactor voltage, circulating current is going to be takes place. Because of large reactor, sudden changes will not allow. Now you can see voltage is high, then current will be gradually build up. Because this voltage is gradually decreases, sudden changes will not allow, and it is build up in this current, and this voltage is 0, and the current will reach its maximum. Then it is developing in the negative voltage, and then current will be gradually decreasing. Once it reaches to the 0, again voltage jumps to the maximum, then current will be gradually. Why current is not jump to maximum? Because large reactor, so this current will be gradually rising, and once again it reaches to the 0 and current will be maximum, then build up the negative, then it will be discharging like this. This is a circulating current. Now what is the I1 current? So what is I1 current is nothing but a I0 plus circulating current. These two have to add. What is I0? Let us assume that load current is constant. That's why I consider load current as a constant magnitude. Now you add the circulating current plus load current will give as I1 current. This magnitude is constant. You add any particular instant constant magnitudes, this total magnitude little bit will be higher than the circulating currents, but shape is same because we are adding with this waveform only. No, this magnitude is 10 means every instant 10 you can add, that's it. So we will get it as a total current. How will you get the controller to current? Controller to current is nothing but a circulating current, because I1 is nothing but a I0 plus I2. That I2 is a circulating current. That is the reason I2 is equal to IC. So that's why whatever waveform is here, same waveform will be presented there. So that is the waveforms. Now as usual derivation, all these things are same. Now it is a three-phase supply. We can make use of VA is equal to Vm sin omega t, and Vb is equal to Vm sin omega t minus 120 and plus 120. Va plus Vb plus Vc is equal to 0. Use all the relation. I will show that anyhow. Now you can see that any particular instant, all the pulses are same. We can able to integrate that portion. So now you can see particular instant means alpha 1 plus 30 degrees to 120 degrees. Each device will conduct as a 60. Each pulse is 60 degrees. Then alpha 1 plus 30 to alpha 1 plus 30 plus 60. So that is a 90 degrees. So alpha 1 plus 90. Up to that instant, I am considering as a output voltage waveform. That magnitude is what we noticed in that that value we can consider. Now you can see that in that duration we started here. The duration is VAB for V01 and the V02 case VBC. And similarly, you are using that VA, VB, VC as usual equation. And if get the line to line voltage, AB is nothing but VA minus VB, VBC is VB minus VC, like that. You have already done this in case of three-phase full controller. And now VDC1 under that instant. What is the instant we consider? Alpha 1 plus 30 degrees to alpha 1 plus 30 plus 60. That means 90 degrees. Under that, what is the VDC1? What is the VDC2? What is the reactor voltage? Subtract these two things and we'll get it as a VR is equal to minus 3 VB by subtracting this VAB VDC1 is VAB we observed, and VDC2 is VBC, and subtract this 2, we'll get it as a minus 3 VB. And now we are integrating this. VR is nothing but LdI by dt or LR, whatever you notation you want to follow. L is here is not a load inductor, it is a reactor. So IR or IC, circulating current, minus 3 VB is Vm sin omega t minus 120, and integrate both sides and simplify that, we'll get it as a circulating current is equal to this one. Once if you know the circulating current expression, any particular value of alpha, suppose the mass alpha is equal to 45 degrees, what is your circulating current? Put it here, we'll get it as a circulating current, that is a peak circulating current. This is general expression for circulating current, peak circulating current, we can use this formula like this. And there is advantages and disadvantages as usual. I mentioned no, in the previous case of CC mode, we don't require to wait 10 to 20 milliseconds of time. Power can flow either direction because of both controllers operating at a time. The time response of the changing from one quadrant to other quadrant is faster because only changing the alpha, any one of alpha is changed automatically other. And disadvantage is also there because of the reactor. I already told reactor is required to limit the circulating current, so the size of and cost will be high. More losses because of the reactor, hence efficiency will be low comparatively NCC mode of operation. Handle load current as well as the circulating current. That's why thyristors we have to use high rating thyristors because additional circulating current is. So there is one important question, comparison between the circulating and all I mentioned here, whatever I discussed the previous points, all the things I mentioned, it is very normal points what we discussed. Only one controller operate, here both controllers will operate in discontinuous mode because waiting time is there, and here is a continuous mode of operation. A reactor is required because to limit the discontinuity problem, or in this reactor is not required. You can mention directly reactor is not required, but here reactor is required to limit the circulating current. No circulating current, that's why efficiency will be high and efficiency will be low. So due to that, the 10 to 20 milliseconds of time, discontinuity current will be problem. So that is a non-linear transfer characteristics, and here linear transfer characteristics will be obtained. And then response will be slow, and here response is fast. Then we required this time, but here is not required, both is operating at a time. This will be cheaper because of the reactor is absent, and here is a little bit expensive. So all whatever points we discussed, that you can make it. And now you can see the problem also same, whatever formula we used there, same problems. You can see there is a single phase or a three phase, only formulas will change. Dual converter supply 220 volts, and it is R is equal to 20 ohms, and L is given as a 0.08 Henry. Alpha 1 is 45 degrees. Find the firing angle of controller 2 and average value of load voltage and peak value of circulating current of both controllers. Now you can see first bit is straightforward. Controller 1 alpha is given 45 degrees. Then automatically controller 2, what is the alpha? 180 minus 45. That is the first bit. Then what is average voltage? We are integrating that. That is as usual of average voltage is nothing but a 2 Vm by pi into cos alpha only. 2 Vm by pi into cos of alpha 1. Controller 1 alpha is equal to 45 degrees. That's why 2 Vm 220 is given, root 2 into 220 by pi cos 45 degrees. That will give as a controller 1. And circulating current, already we derived the expression 1 minus cos of alpha 1. So 2 Vm by omega L 1 minus cos alpha 1. Then direct substitution 2 into root 2 into 220 by omega is 2 pi f, and L is given 0.08 Henry, and if we substitute that, we'll get it as a ICP, that is a peak circulating current. Then how will you get the load current? Load current is nothing but a voltage by resistance. Voltage Vm by R, the load resistor 20 ohms is mentioned, and Vm is root 2 into Vs, that will give as a 15.556. Another one, the controller 1 current. What is the controller 1 current? Output current plus circulating current. That if you add, will give as a controller 1 current. What is controller 2 current? Nothing but a circulating current. Controller 2 current is equal to the circulating current. We already calculated the circulating current here 7.254. So controller to current is nothing but a circulating current. So like this we can do for the 3-phase also. I mentioned all the formulas, problems also is specified here. And again you can see that some other alpha 1 is 50 means automatically alpha 2 must be 130 degrees because 180 is that. So like that we can same formulas, nothing else, 1 minus cos alpha 1 and converter 1 current output plus circulating current, converter 2 will be the same as that. So I mentioned some more problems also I given for your reference. You can solve these problems. In external exam there must be as a problems. You should not leave that problems. In each question another A bit is theory, B bit will be problem, like that. Problems are very straightforward. I given all the problems in the LMS server also, and later I will share some of the textbooks also if you want soft copies of that you can refer, or in library also many textbooks are there. Practice the problems because somebody in mid one they solve the problem, but only the problem is in that suppose formula is 2 Vm by pi into cos alpha. How to substitute that 2 into Vm means it is not a supply voltage, it is a peak. So root 2 into Vs, that's many people are forgot to use the root 2 in the mid one. So mid one performance is very poor. I given direct problems, that all problems are I shared to you in the previous PPTs, but in that problems only I given, but many people are unable to attempt. And I asked the firing triggering circuit. Triggering circuit means R or RC or UJT, like that. Any one I asked, but many people are asked turn on methods. Turn on methods is different, triggering circuits is different. There is a firing circuit or triggering circuits are R, RC, UJT. Turn on methods are forward voltage triggering and dV by dt triggering, temperature triggering, all these things is turn on methods. So that you can take care of that, and you can refer the old papers. Many papers are available. You just Google it, power electronics question paper, how they are asking, what is answer you need to write. If you have any doubt you ask me. At any point of time you come to my room and you can ask, or at this end of the class also I am waiting sometime now for doubt clarification, but nobody is asking. We have any doubts how to write anything, you can ask me. So this is end of today's class. If you have any clarification, you can ask me, otherwise you can leave.